Are we okay? So we are recording right now, right? Okay, cool. Okay, thank you everyone for joining. Today we have Dr. Chi. She is a research scientist at Laboratory of Atmospheric and Space Physics. She earned his BS in 2016 from University of Science and Technology of China and completed her PhD in UCLA in 2021. Following graduation, she joined LASP as a postdoc researcher, and she has since continued her work there. And her research primarily focus on magnetic reconnection and associated plasma process in Earth's magnetosphere using observation from NASA Magnetospheric Multi-Scale Mission, MMS. Her broader interests also include reconnection in the solar wind and solar corona, as well as plasma turbulence. So let's welcome Dr. G.
Thank you. Thank you again for the invitation, and it's really my honor to be here to share my study with you guys here at HAO. So the title of my talk is Magnetotail Turbulent Reconnection and Associated Particle Energization. This work is supported by NASA MMS mission, and I'd like to thank the whole MMS team and my co-authors for their support and help. Okay, so first, the outline of this talk. So we'll start from some basics of magnetic reconnection, and following, we'll review some of the textbook information about particle motions and energization mechanisms. Hope you guys won't find it too basic. And then we'll get to the interesting observation part. We'll see one very impressive case in the Magnetotail showing a reconnection EDR crossing with explosive energization process. And then we'll use test particle with both electron and ion to deeply investigate how are particles energized in turbulent reconnection. So first, what is magnetic reconnection? We're looking at this cartoon that oppositely directed field lines coming in together at the center, where we have this current sheet pointing into the screen. And then the field lines here break and reconnect, and they are expelled out from this center region. During this process, there will be energy exchange from the field to the particles, and you will see extremely high-speed plasma flows going out. And that's one of the most well-known signature of reconnection. So this is a very, very simplified picture of magnetic reconnection. Some major questions we cared about reconnection is, first of all, how does collisionless magnetic reconnection occur, and what supports the reconnection going? And here specifically, what supports the reconnection electric field? The electric field point into the field and continues the plasma to support the plasma keep coming in and going out. And the third main question is, how is the magnetic field energy dissipated in this process? So first, to understand how reconnection starts, we need to go back to the very fundamental concept of plasma physics, which is the frozen-in condition. So we know particles, normally they gyrate around field lines like this. And in the frame of the particle, if we assume infinite conductivity, they would not see any other electric field. That's how they can maintain this gyro motion. So E plus V cross B equals to 0 is what we call the frozen-in condition, and particles will be frozen with the field line and move together with the field line. But imagine when you have reconnection, when the fields become really weak at the center of the plasma sheet or the current sheet, at some point, the particles cannot follow the field lines anymore, and there must be some diffusive motion. So in this region, we call diffusion region. That's where the frozen-in condition is no longer valid. So E plus V cross B is no longer equal to 0. Here is a sketch showing the multi-scale nature of magnetic reconnection. So the diffusion region we just mentioned is only the very tiny area at the very center of reconnection here. So first to the left, we're looking at the MHD scale or the global scale. It's often several RE or tens of RE. But when we're looking at the ion diffusion region, it becomes like a region only hundreds of kilometers. And the electron diffusion region, which is the very center of reconnection, is even smaller. It's like smaller than 100 kilometers. So that makes it very difficult for us to study the center of reconnection, the diffusion region, and also makes it very challenging to study the coupling of all these different scales. So what's happening here? So first, we can go back a little bit to, since we already mentioned the frozen-in condition is no longer valid, we need to find a way to maintain the reconnection electric field. So without the V cross B, what other terms we can use to support the electric field? So the very, very old model, the ideal MHD model assumes there is some anomalous resistivity. So we have this eta term. And with this resistivity can be supported, and these are the two most famous models, Sweet-Parker and Petschek. This model explains how electric fields maintains there, and also we have finite energy conversion, J dot E, non-equal to 0. But there is a major problem with this old MHD models, which is the reconnection rate is often not high enough. So that's why later times we developed HAO MHD, or naturally our theory went into a smaller scale. When we go into the ion inertial scale and we look at the HAO, the Ohm's law, we find when the scale is small enough, the J cross B term becomes large enough to support the electric field. And what happens in this scale is we have ions already demagnetized, but electrons still magnetized. So they're still following the field lines flowing into the current sheet. So this separation of motion will naturally give you currents like this in this quadrupolar pattern, which is known as Hall currents. And of course, you will also have a Hall magnetic field in this pattern, and also Hall electric field, which is because electrons are going in, so you will have the electric field pointing towards the center of the current sheet. Those are the characteristics of reconnection at the ion scale, or you will often see them around the ion diffusion region. And going to the smaller scale, and the reason why is because even though the HAO MHD is a step forward, a very major problem it still cannot solve is since the E is provided by J cross B, so J dot E is still equal to 0. There is no energy conversion, even though you considered the J cross B term. So to have this energy conversion, we go to the electron scale and find the divergence of the electron pressure tensor is actually playing a very important part in supporting the reconnection electric field. On the bottom right here is how to say, it's a cut through the X line showing the different component of the electric field contributor. And you can see right at the very center, the biggest contributor is from EPY, which is the divergence of the electron pressure tensor. And also this hypothesis has been verified by the MMS observation back in 2016. This is our benchmark paper showing the electron signatures observed in the reconnection region. And you can see this 2D electron distribution function has this non-gyrotropic crescent distribution, showing this non-gyrotropic pressure tensor. Okay, another relevant concept that we already talked about is the reconnection rate, which is the reconnected magnetic flux per unit time per unit length of X line. And oftentimes it is equivalent to the reconnection electric field. So with proper normalization, it's very interesting that in almost every case, everywhere, it is almost always 0.1. So that is a very fundamental characteristic of reconnection as well. Okay, we've been looking at reconnection from mainly the field's perspective. Now we can move to look at how particles react. We start from the particle motion equation, and we can divide them into the part that's parallel to the magnetic field and the part that's perpendicular to the magnetic field. So the simplest case would be we just have this homogeneous uniform magnetic field, right? And the particles would just gyrate around the field, which is the gyro motion. So that's one of the simplest case. And for the parallel direction, the simplest case would be we just give it a parallel electric field. And that parallel electric field can accelerate or decelerate particles along the direction of the field line. So those are the two very basic motion for particles. So now we make the case a little bit more complicated. We add perpendicular electric field to the particle. How would it react? And anything else in the perpendicular direction that would contribute to the drift. So those are the a little bit more complicated case. Here is a summary. So with the additional perpendicular electric field, we will have this E cross B drift. Ions and electrons are often go to opposite directions, go to the same directions, but they gyrate in different senses. And depending on their velocity and the drift velocity, you will have different orbits like this. And now we consider a not uniform magnetic field. So if the magnitude of magnetic field changes, you will have the gradient drift going like this. And if the field line is curved, you will have a curvature drift, can be described in this. So those are the very well-known drift velocities contribute to the perpendicular part of the particle motion. Combine all those together, we will have a more realistic objectory of the particles in the magnetotail. So this is the XZ plane of the magnetotail, and the plasma sheet here is oftentimes very similar to a Harris current sheet. So you have magnetic field lines decrease towards the center of the current sheet. And in this case, while the particles are gyrating around the field lines in the low, when we get closer to the plasma sheet, they'll start to feel the change in the magnitude of field line, magnetic field, and they'll start to do the gradient drift. And when they actually see the field reversal at the current sheet, they will have this kind of like a serpentine motion of orbit depending on the angle when it goes into the current sheet. So with all this combined together, we'll have the Spicer orbit that describes how the particles can follow the field lines to enter the crosstail plasma sheet and then goes out into the curvature drift. So that's, we'll talk about this a lot more in the test particle simulation. So this is just a background showing to make sure we're on the same page. And a little more on the adiabatic acceleration. So we all know while particles are doing the gyro motion, the magnetic moment is conserved. So the conservation of this mu also will give you the Betatron acceleration, which means if the magnetic field changes, the magnitude of magnetic field changes, the velocity of the particle will also change. And that happens in the perpendicular direction. And the second adiabatic invariant is J, which is if the particles are mirroring in this magnetic mirror, that bounce between those two mirror points. If the length of the magnetic field line changes, the parallel velocity of the particle will also change. So the J is conserved. And that is the Fermi acceleration, which will result in the velocity change or energy change in the parallel direction. And the third one is the drift motion, which is the conservation of the total magnetic flux in this drift surface. And we also know there are limitations for those parameters to be conserved. And there will be times, especially in turbulence, that even the magnetic momentum cannot be conserved and things will get a little bit tricky. So hopefully we're not too confused at this point, and I would just want to show this map of all the particle motions in the context of magnetic reconnection. So here again, we have this X-line geometry of magnetic field. Here at the very center, going out of the plane, we have the classic Spicer orbit. And here, if you happen to have some islands, there can also be Fermi acceleration happening in those plasmoids. And at the separatrix, that's often where we have parallel electric field. You can see acceleration of the particles by the parallel electric field. And also, since we have the magnitude of magnetic field changing, you can also observe Betatron acceleration. And also, the Fermi acceleration of the electrons are shown here. So this is the particle motion in the context of X-line. Now we're making things even more complicated. We're adding turbulence to the system. So simply put it this way, turbulence is the system, or turbulence cascade energy from large scale to small scale, right? Interestingly, at some point, like at electron scale, there can be processes that make the energy cascade go inversely. Like, I think a simple case would be, imagine two flux rope merge into a bigger one and energy exchange happen during that processes. So oftentimes in the turbulence, we have energy injection, and also you will need a dissipation mechanism to sustain the energy cascade. So there are some common ways to dissipate the energy through resonant wave particle interaction, like the classic Landau and cyclotron damping, or non-resonant wave particle interaction. This part we'll talk more later too, stochastic heating by the random fields. And also we have dissipation and at intermittent coherent structures. That's often referring to reconnection happening at those very small scale current sheets in turbulence. So that's about all the backgrounds and terms we need to know. And to study the reconnection electron scale signatures, before MMS, it was really difficult because we don't have instrument that can look at such small scales and have high enough time resolution. And especially we cannot differentiate the temporal and spatial differences. So MMS is 4 identical spacecraft that's really closely located to each other. Like the smallest separation of those spacecraft can be like 7 or 10 kilometers. So that's really targeting at the electron scale. And during the prime mission, MMS apogee is at this 2' reconnection location at the day side and at night side. So our main goal is to investigate the electron diffusion region and ion diffusion region characteristics of reconnection. Some instrument we used for this study, the magnetic field is from flux gain magnetometer, and the plasma mostly from the fast plasma investigation. So the energy range for this instrument is from 10 eV to 30 keV. They have a slightly different resolution for electron and ion, but most time this is enough for us to investigate the kinetic scale physics. And for higher energy particles, we'll use the instrument known as FEEPS. And here we can have energy coverage from 20 keV to over 600 keV. So this will really help us investigate those very energetic particles in the tail. The first part of the study is a case study, which really triggered our interest. So this just some overview for this case and why this is so special. So first of all, it happens in the Magnetotail, and we can see from the cartoon here, MMS trajectory goes from the north lobe to the EDR and then goes to the south. On the right-hand side, we have an overview plot about 47-minute. So the blue trace here is the sorry for the label, is the BX component of the magnetic field. So we see it reverse from positive to negative, showing it's a transverse from north to south lobe. And during this 47-minute, the last panel shows you the ion velocity, and we can see the blue trace, which is also the X component, has several reversal marked by the perpendicular line. So oftentimes the ion jet reversal is a good indicator for reconnection. Not necessarily electron diffusion region, but whenever you see an ion jet reversal in the tail, you often know at some point there is reconnection happening. So at the center, right around the second ion jet reversal, we enter this region, as you can see from both magnetic field and electric field. The fields start to become really turbulent or dynamic. And interestingly, if you see the plasma density, number density, right when you go into this turbulent area, the plasma density like sharply decreased to a very low level. And while this is happening, we see the electron and ion energy just like shoot over the roof. And we can see here for the ion, it's even like going out of the range for the most used FPI instrument, and most of the energy is in the high energy instrument, FEEPS. So this is, before I highlight the special part, let's just look at the overview or the zoom in around this interesting reversal too at the reconnection current sheet. So again, we can quickly review some of the reconnection signatures. Here is we rotated into a local coordinate system, but simply put, we can see the reversal of magnetic field. Shows you here is the current sheet crossing. And at the current sheet crossing, this blue trace shows the very strong Hall electric field caused by the separation between ion and electron. And the blue trace, the M component, is the important reconnection electric field we've been talking about. It's like overshadowed by how large the EN component is, but the EM here, the reconnection electric field, is extremely high for a tail case like this. The magnitude is 4 to 5 millivolts per meter, and it's about twice as big as most reported tail EDR. Like we mentioned, the number density is extremely low, and right at the current sheet crossing, we have a strong electron jet in the out of plane direction, which is carrying the current. And the red trace for the electron velocity is the reversal for the electrons. So it's telling us the electrons are also being accelerated. And the last panel is the energy conversion, J.E. It's also really large. Like all the things highlighted on this side makes this event stands out from the rest of the tail EDR that's being seen.
So this one is the same as the previous event, just zoom in.
Yes.
Okay.
So this is around the second vertical line.
Oh, okay.
Yeah, just zoomed in. So you can see the time span here is only like 10 seconds, 20 seconds-ish. So it's really zoomed in at a small scale. So yeah, really large reconnection electric field, really large energy conversion, extremely low plasma density. Everything is suggesting this event is like a reconnection event in the tail that's going crazily. Like there's super high energy conversion happening here, right? But why this is important? Why do we care about it? So in my opinion, I think what's important is not locally, because locally, if you normalize the electric field, the reconnection rate is still around 0.1. So it's still like regular. But if you go into the lobe, since the energy keeps going into the reconnection site, and you don't have a J.E to balance the Poynting flux, what end up is you will suck all the lobe energy into the plasma sheet, and that will have a important, I think, global impact. if we have a strong reconnection going on in the tail like this. And locally, there are also interesting aspects for events like this is we often see much higher Hall electric field in tail events. And we're confused, like why in the tail events, we often develop a stronger electric field in the normal direction. And a possible way is we need to, like, since we have so much energy coming in, we need a way to get them out of this region, right? And to support such a high pointing flux, we can develop a stronger EN. So you can imagine the stronger EN can be like a regulator to ship all the inputting energy out to maintain the local reconnection behaving the regular way. So this is some interesting aspect for this event and why we think it is important in the global for the global environment. But what I find most interesting is how do we end up getting all those energetic particles? How do we get those, like, we often say they're the tail, the energetic tail or the non-thermal tail. It's because if we consider a normal distribution of the particles, they will be Maxwellian. But when they're energized, sometimes you will see this population at the high energy part showing up. So the total particle distribution is no longer Maxwellian, and we refer to those energetic particles as the non-thermal tail. So how can we have those energetic particles with reconnection in turbulence is the question. So we propose this near runaway effect. So what's happening is when reconnection first happened in the tail plasma sheet, it naturally, because when it happens, the lobe flux keeps coming in, and the lobe is naturally has lower plasma density, and it's like weaker plasma in general, like colder. So you will have a natural decrease of the plasma density at the center of the current sheet. And what that means is each pair of the particles will have to carry or absorb more energy when there are fewer and fewer of them, right? If the reconnection keeps going. So if you have the density keeps going down and like a constant energy flow coming in, each particle will get energized more. And at some point, if the energy cannot be absorbed in a linear way, you may have turbulence develop. And there are previous studies showing with strong turbulence, it can further help the decrease of particles density and give you this loop that positively feedback that you have fewer and fewer particles in this region, like we observed by MMS, and each of the particles are energized to higher energy. It's like a near runaway effect to give you this non-thermal particles. So that's just a hypothesis. And starting from this one case study, this is just in case you're curious how turbulence can assist to decrease the particles density. We have a study that's under review currently that explains how this can happen. And if you're interested, please keep an eye on this paper. But starting from that one case, there is a survey study by Wang et al. They actually surveyed 16 turbulent reconnection events like this, and those 16 events have varying magnitude of turbulence. And what they mean by the degree of turbulence is how strongly are the magnetic field fluctuating. So they're using the delta B RMS as a parameter to describe how strong the turbulence are. And what they find through the study is when you have a stronger turbulence, you end up having have lower particle density. And at the same time, the electron temperature becomes higher. So that kind of agrees with what we see in the previous case study. And also, this case their survey shows while you have a stronger turbulent level, here is showing the frequency, but you can understand it in the spatial space. So you will have a smaller scale length in your system while you're having a higher magnitude of the turbulence. So this is what we see from MMS. And now we're curious, like how does the magnitude of the turbulence affect the energization processes, right? And we're curious, what is the dominant energization mechanism? Because there is always a debate, like what is the dominant acceleration or heating mechanism for plasma in the turbulence with the existence of reconnecting current sheet. And it's often considered Fermi acceleration is very important. So that's something we're going to investigate using a test particle simulation. So for the test particle simulation, we're using observed parameters to set up the background and initialize the simulation. So this event, similarly to what we just discussed, it has a, so we're looking at the overview. So again, magnetic field here, we're crossing from the south of the lobe, as you can see from the negative BX, the blue trace here. And then we entered into a turbulent region, and we're going out. And in this turbulent region, there are ion flow reversals, again, showing by the blue trace here, indicating reconnection is happening. And again, right when we enter the turbulent region, the plasma density start to decrease, and you see the simultaneous enhancement of the particle energy. So this is a similar case as we discussed, but it just doesn't have, we didn't cross the EDR in this case. That's why it doesn't, we didn't use it as a showcase. But this gives us an idea of what the background looks like. What the environments look like. So we're going to use this event to do the initializing. And here is our simulation box. What's impressive about this simulation is this is the test particle simulation, but it is three-dimensional and it has open boundary, which is really important to study energization processes. Because if you have periodic boundaries, you have particles like reflecting back from the boundaries, right? And that can give you some artificial energization, in my opinion. So very importantly, 3D and open boundary. And we just added the magnetic field to look like reconnection. And we added the reconnection electric field, EY, here. So the reconnection is naturally happening. We just we force the geometry of the field line to look this way. And so we can investigate how the particles react to the geometry. And on top of the reconnection current sheet, we also use the MMS observation to reproduce the as realistic as possible turbulent fields. It has both magnetic, electromagnetic part and also electrostatic parts. So this solves the problem in most other simulations because we already have very advanced PIC simulation or HAO and NCAR simulation. Why are we using test particle? The major reason is in all those simulations, we cannot reproduce a realistic magnitude of the turbulent electric field, which is a very, very important factor that will impact the energization processes. So this is probably the first time we're able to see how the particles react to realistic electric field magnitude in the turbulence in this test particle simulation. And here is a validation plot showing with this configuration, we can have a very similar particle distribution as we observed by MMS, showing we're doing a good job reproducing everything. Here's just more validation, shows the temperature is also similar to what MMS observed, and you see a decrease of the plasma density like we have seen in the previous cases. And now get to the interesting energization part. What we're looking at here is the plot along the Z position, like across the reconnecting current sheet in the normal. So the color represents the normalized counts, but the y-axis here showing the net energy change. So we see particles like they sometimes give energy to the fields, sometimes the fields give energy to the particles, nothing abnormal. But if you do the net like to sum all the energy change together, you have this magenta line showing a very significant positive peak around the current sheet at z equals to 0 position. And overall, even you go out of the current sheet, it's still like a net positive, just smaller. So this net positive energization shows there is second order stochastic heating happening in this system. And to achieve this, we need to consider both Spicer-like orbit and also the stochastic processes in turbulence. And since we're in the simulation, we can play with the magnitude with the turbulence. We can completely turn it off to have a simple planar reconnection case, or we can turn it on to have a full turbulence. So now we're looking at the displacement along y. Oh, sorry. So imagine if you only have the reconnection electric field EY, all the energy gain will be from the displacement in the y direction times how strong your electric field is, right? So you will have a straight line going up along y direction, showing how much energy you gain from the EY. But interestingly, when we turn turbulence on, you see the data points just scattered all over the place. And if you look at the value, like the largest value you can get from the reconnection electric field is like 50 keV. But when you have turbulence, they can easily go over 200 keV. So they're gaining energy from somewhere else instead of just from the out of plane electric field. And it's like in addition to like the enhanced total energy gain, there is an additional portion showing up when we turn on the turbulence, which is this part, about 80 keV. So when we have no turbulence, this part is completely disappeared. So this part, this non-thermal tail energetic not electron ion, is a new population caused by turbulence. So now we use 80 keV as a threshold to consider particles above 80 keV. We think they are caused by the turbulence energization, and particles below is like kind of normal way. That's how we can make a plot like this. So now the x-axis is the turbulence amplitude going from 0 to full amplitude. And the y-axis is the energy gain. So now we separate the particle below and above 80 keV, and we can see while we're turning up the turbulent level, we have an increased population of the 80 keV particles. And this part should be constant, but there might be some numerical problem that makes the line going down a little bit. But yeah, the major point we're trying to make is the turbulent amplitude will affect how much non-thermal energetic particles you have here. And of course, the length of the X line will also affect how energetic they can get. But the amplitude of turbulence is really important to change the ratio of the turbulence to Spicer-like energization. And then the previous part is for ion. We repeated the same thing for electron. And here we can go a little bit deeper and look at the particle trajectory and the mechanisms for parallel and perpendicular energization. So here again is a validation showing the simulated particle or field spectra agrees with the observation. So we're trying to redo what we see in the MMS data. And the result one is showing the lower particle energy. It's from about 10 EV to 30 keV energy range. It's in this part in the particle distribution. And we're looking at a 2D cut for the distribution function, the perpendicular and parallel. And the very interesting feature here is in both simulation and observation, we can see the particles are energized in the parallel direction. Like you can see it's no longer a circle, but elongated in the y direction, showing for lower energy particles, they're experiencing energization mechanisms that favor parallel direction. And on the other hand, when we look at higher energy particles, they're experiencing a much higher perpendicular energization. So there are different mechanisms that works on particles of different energy. So they're not always undergoing the same mechanism. And to look, so again, we review this map, right? There are so many different kinds of trajectories we can have in the complicated system. So in our test particle simulation, we have all of them almost, except for the Betadron acceleration. Not know exactly why, but I think it's because the Betadron, like we're in a turbulent environment and like the field magnitude just goes up and down. So the particle just like give energy to it or receive energy from the field. So the overall net influence from Betadron is very small. But we do see all the other acceleration mechanisms in the test particle simulation. And we'll be focusing on the Spicer orbit, which is at the center of the X-line, and also the Fermi acceleration, which is more towards the edge of the EDR or IDR. So this is a map showing the summary of the sum of the total energization at all the times. So we can see again, with the top one is without turbulence and the bottom one is with turbulence. And the center region in this dashed circle, we identify it as the Spicer region, which means when particles enter this region, they are demagnetized enough to go under the Spicer orbit. And this other two location are the parts that the particles often goes Fermi acceleration. And with turbulence, at first glance, you may think, oh, Fermi plays a really important part because you have the reddest region here. But later, with further investigation, we'll show this Fermi parts is, they look like they contributed a lot is only because you have a denser plasma in those regions. But they actually contribute more to the thermal particles, which is the lower energy part. Because remember, Fermi is also responsible for the parallel energization, right? And we do see the lower particle has a higher parallel velocity. And the center part, which looks like it's less important, but they actually contribute to what we call accelerated electrosphere, which is the part of the particles in the distribution that's in the tail, accelerated tail, the energetic particles. And we can trace all the particles to see how individual particles move in the test particle simulation. And here is a very simple, like a single Fermi. Particles enter here, enter to not quite at the center, and then become reflected. And we can also follow the energy gain in this process. And we find it's not very much. Like there is one energy gain from the curvature drift, like less than 1 keV. So it's really not that significant when we're looking at hundreds of keV electrons. And okay, people are going to say, what if we do multiple bounces? What if we let the particles to go back and forth? Can we get multiple acceleration? Yes and no. So we have one orbit showing here. The particles are undergoing multiple Fermi, but when you trace the energy gain here, we can see the actual energy gain is actually only from the initial curvature drift. And then, yes, it's mirroring, it's going back and forth, but it just do this energy gain and energy like back to the field lines back and forth. So an important criteria for particles to gain energy through multi-Fermi is you have a contracting magnetic islands. That way you will have a shortening field line, and by bouncing on this shortening field line, you can have particle gain energy through Fermi. But without the contracting magnetic islands, like in the case here, we'll still see, even with multiple reflection, particles still only receive very few energy. And then the Spicer drift, those are for the particles that goes really into the center of the reconnection line, so they can be demagnetized and go in the out or in the plane direction. And different from the Fermi, we can see the energy gain is easily to 20 keV, and that's like an order larger than the Fermi acceleration. So this is a classic Spicer drift. This will happen even without turbulence. So what turbulence does is they will boost this kind of Spicer drift. And what I mean by boost is, for example, this one, we see the particles coming in, but they didn't quite enter the Spicer region that we mentioned before. So normally we think, okay, particles are still magnetized. It's not going under the Spicer orbit. But with turbulence, you can imagine it as it expanded the demagnetization layer. So in the larger area, particles can go under the orbit, kind of similar to the Spicer orbit, and gain energy through the out-of-plane electric field and also the stochastic acceleration by the turbulent fields, like shown here. Also, we can easily get 20 keV energy. Another one is a fully chaotic orbit, showing how particles are just dumping around in the turbulence. And this one just shows how significant stochastic heating is contributing. Like you can see at the bottom panel, the stochastic heating is almost twice as large as the energy particles can get from the out-of-plane electric field. So it's a major contribution from turbulence, just from the stochastic random walk heating. And with all the orbits, we can get a plot like this. Again, we're looking at the influence of turbulence amplitude. We can increase it from 0 to full turbulence, and we can separate the energy into different ways. For example, the blue line is energy from the electric field out of plane, and without turbulence, you will have zero stochastic energization, which is the red line. It's 0 when the turbulence is 0. And you can see when the turbulence is turned up, you have a higher and higher stochastic energization from turbulence. With full turbulence level, you have like 2/3 of the total energization coming from stochastic heating. And then we can further decompose the energization from electric field into the Spicer orbit or the Fermi reflection, because they're both essentially caused by the out-of-plane electric field. So we can imagine the blue line becomes the total of the magenta line and the green line here. The green line is the Spicer energization, and we can see with an increasing turbulence amplitude, the green line, the Spicer kind of enhancement is also enhancing a little bit, but not much. The Fermi reflection kind of saturated because at some point it just become 2 times the cross V velocity. So we use a dashed line to kind of predict how much it can get, because when you have a too high turbulence level, it's become harder to trace all the Fermi trajectories. So you would imagine the blue will equal to the green plus magenta, but interestingly, when the turbulence level becomes higher than 0.2, there's a discrepancy between the total of Spicer region plus Fermi reflection and the total energy gain from the Y electric field. And that's what we call the turbulence boosted acceleration or energization. And it's showing here by this orange trace. Okay. And coming back to how to get energetic particles, the tail part. So we're talking about the total energization, right? But why the energization favors high energetic particles to form the tail, or why there is a favor in the perpendicular direction. The key is the scale length of this of the turbulence or the fields. So it's a result from a previous study on turbulence. So just long story short, when the frequency of the fluctuation of fields is small, we can show the correlation length or the scale length of the fields are at the ion scale. But for a higher frequency, we have the length scale sharply decrease to electron scale. And what happens when you have a correlation length this small is you will end up having, for example, if you have a high enough parallel velocity, when the particles are following the field line this way, but it's really fast, you may be able to see different regions of electric field, right? Because the scale length of the electric field is really short. So what happens is you will get energized in those different directions instead of like a complete circle and you just like maintain the total energy constant. So this is when you have a high enough parallel velocity, you will get a strong perpendicular energization by the EPERP. And if you have a large enough gyro radius, which is high enough perpendicular energy, you will also see different regions of electric field. And again, you get kicked in different directions and get even higher energy. So it is what they're often joking, like the rich get richer case. Like when you're already energetic, you actually got more energization from the turbulent field simply because the scale length. And in this case, the magnetic momentum is no longer conserved. So it's really hard to use the guiding center assumption to try to characterize all the energization processes. And this is just like what we said, the rich get richer case. When you have a higher energy, you actually get more energization gain. So I'll stop here. I'll leave the summary on the screen and I'll be happy to take questions.
When my understanding, like when the very strong is happening, it could potentially have a mesoscale impact, also have a global impact. Like I wonder if you have like simulation inclination, like say from turbulent scale to mesoscale and then to the global scale.
It's really hard.
Yeah.
I think that. Yeah, like I said, like we already have 3D PIC simulation or PIC embedded in MHD, which is suitable for what you suggested, right? We can start from the very small scale physics and study how the global responds to that. But a major problem involving turbulence is they cannot produce the right electric field magnitude. So it's really hard to examine that specifically. But if you're interested in general reconnection, global reaction, I think there are already plenty of study showing like you may want to look at papers with bursty bulk flow or depolarization front with words like this, and they often have a conjunctional impact in radiation belt or even ionosphere. We just have this substorm onset discussion at GEM. We have a lot of ionosphere folks also interested in this whole conjunction thing, because ideally you'll be able to use aurora to trace what's happening in the tail. So it's also a very interesting study area.
So I wonder the way like you do your PEG simulation, what's the boundaries look like? Like, is it coupling from small scale to large scale? Like use small scale as input, or is another way around? Use larger.
Yeah, I think I'm not an expert on the PIC embedded MHD, but I think they use MHD as the boundary to set the PIC.
I'm just curious, like, is there any co-observation between MMS and other mission, like more close to
Yes.
open mission?
Yes, another researcher in my group is studying bursty bulk flow using MMS and Venice. So
Okay.
ideally, we want to see what's the extent of the crosstail X-line, right? So if say MMS and Venice has a really large separation in Y, and they both see the bursty bulk flow, that probably means we have a very continuous large scale X-line in the tail. But if they don't see them at the same time, it probably means the X-line is patchy and either in space or time, like it happens and stop.
Okay, so I just have a very naive question. So there's already some case that already being observed. Is that true?
like a conjunction?
Yes.
Yes.
Okay, cool. Yeah. Any other questions?
In your observations, you show that there is a decrease in number density in the X line. This feature is specifically for this lobe or magnetic tail reconnection, or this feature is just global for every other type of
Yeah, that's a really good question. So it's not uncommon for tail reconnection to see a decrease of plasma density because if you have lobe plasma involved, right, you can imagine. But what's special about turbulent reconnection is they're much lower than the other cases. Or we think the hypothesis is also it happens or the turbulence develops when you have a low plasma density. So yes and no to your question.
Okay. Okay. If there's no other questions, let's thank our speakers today. Thank you. Thank you.
Thank you. That was really interesting.
Thank you.
So,